Hello, so today we're going to be doing the notes called Seeing is Believing, and this is a part of the differential equations group of notes. So we're going to actually be looking at slopes today. If we look at number 1, we have a differential equation, dy dx is equal to 2x. So from what we remember about graphing and derivatives, a derivative is a slope on a graph. So basically 2x is a formula for finding the slope at various points. So we're going to be looking at the following 16 points here in the chart, and we're going to be finding the slope of each of these points. So at this point, negative 2, 2, if I use my slope formula, which is 2x, right? I'm only going to use the x value though because there's no y value, so I'm going to plug in negative 2 for x, and we get a value of negative 4. So we're going to be finding the slopes at all of these different points here. So now would be a good time to pause the video and go ahead and fill this chart in, and then you can unpause and pick right back up so you can check your work. Okay, so the slope at each of these points are negative 4, negative 4. The next 4 points are negative 2. Then we have 0 at the bottom there. And then the next 2 points in the next column are both zeros. 2, 2, and 2. And then the last 3 points have a slope of 4. So what we're going to be doing is using this, what looks like a dot graph here. So it's just a bunch of dots on a graph, and it represents a bunch of these points that we have. So we're going to be looking at the points, finding them. So for negative 2, 2, that's right here on the graph, I'm going to be drawing the slope of negative 4. So what I'm going to use is a toothpick, and I'm going to probably put my toothpick right about there. That is about a slope of negative 4, and it goes through my point negative 2, 2. So I'm going to draw a little line that represents that slope. Okay, so I'm going to do that with all of these points. So for negative 2, 0, that also has the same slope. Negative 2, negative 1 has the same slope. And then negative 1, 2 has a slightly different slope of negative 2. It's not quite as steep, but it's still negative. Negative 1, 1 has the same slope. Negative 1, 0. And negative 1, negative 2. Okay, the next couple of slopes are all 0. So 0, 1 has a slope of 0. 0, negative 1 has a slope of 0. And 0, 0 has a slope of 0. 1, 1 has a slope of 2. So if I line up my toothpick and find approximately the slope of 2. 1, 2 has the same slope. 1, negative 2 has the same slope. And then the last 3 have slopes of 4, so they're slightly steeper. So 2, 1 has a slope of 4. 2, 0. And 2, negative 1. So we could keep going. We could find the slopes for all of these points and kind of figure out what shape these make. Now this is called a slope field, this whole thing. And it's a representation of what the original graph probably looks like. And it shows the family of solution curves. So what we're going to do is, if I had to draw an estimate of what a solution curve might look like, if I look at this, it looks like it's kind of waving in like a U form. So if, let's say I wanted to draw the point, the graph that went through 0, negative 1, it would probably look something like this. So it levels off right in the middle. The slope becomes more steep as we go toward the ends. Now I could draw one up here and get another solution curve, or another solution curve down here. So there's technically an infinitely many solution curves that we could get. And that's because we don't know the actual point that it crosses through, and that depends on your value for C. Okay, so we've been solving these so far, so we're actually going to take that derivative from up above here, and we're going to solve it. So I'm going to write that down for number 5. dy dx is equal to 2x. So if I want to solve that, oops, first thing we do is separate the variables, right? So dy is equal to 2x dx. Then the next thing we do is we take the integral. So the integral of dy is y. The integral of 2x is x squared plus c. Now that should make sense because what we drew up here in the slope field were some parabolas, and x squared is a parabola. And the c represents the individual, the particular solutions. Okay, so let's flip to the back. We're going to write a couple important things that we want to remember when we talk about slope fields. So a slope field is a graphical representation of a differential equation, and it allows us to visualize a family of solution curves. So it's a visualization of a family of solution curves. So what you're going to want to do is calculate the slope at different sets of ordered pairs. And then you're going to want to use your short little line segments to plot the slopes. Now, sometimes you might get a slope that's undefined. So let's say you get dy dx is undefined. So typically on a graph, if you have an undefined slope, that means either the graph doesn't exist there, maybe you have a vertical asymptote, maybe there's a hole in the graph, so therefore you do not want to draw a solution curve where you have an undefined slope. Okay, so for question number 1, we have a bunch of points, and we're going to be drawing slope fields for these differential equations. And there's a bunch here. Now on an AP exam, they wouldn't give you this many points. They would probably give you maybe between 6 and 10 points. And you're just going to take a point. So maybe I want to start with 1, 1 here. And I plug it in to my equation, which just needs y. So my slope at 1, 1 is -1. So I'm going to draw a little mark that represents the slope at 1, 1 is -1. Now if I pick a point maybe down here, which is -2, -1, my slope is +1. So it actually only matters what the y value is each time. So for example, if I pick a point over here at 2, 1, my slope is -1. If I pick a point at 2, -1, my slope is +1. So all of these slopes right here are +1. All of the slopes right here are -1 because they all share the same y value. So if you want to make a list and do it this way, that's fine. If you just want to figure out patterns and do it that way, that's fine too. So if all the y values are 2, my slope is going to be -2, so a little steeper. Now in class what we would do is I would split this up into groups, have each group do a couple points to check. Now if my y value is 0, my slope is 0. And if my y value is negative 2, my slope is 2, so a little bit steeper than the 1. Now in the AP exam, they're not going to be super picky about how steep your lines are. As long as it's a positive slope, it should be positive. If it's a negative slope, it should be negative. So they're going to just check to make sure it's going the right direction. So if I'm going to skip down to number 2 real quick, then we'll go back and do the second graph here. But number 2 says we're going to sketch a particular solution that passes through 0, negative 1. So I'm going to find that point, and it looks like the curve kind of goes like this now and levels off. So I'm going to draw a line just like that. We have a steeper slope, and then the slopes go towards 0. It has to be a function, so I can't really draw anything up top here because then it wouldn't pass the vertical line test. Now, if I was looking for a solution curve that went through like this point, then I would draw a line up top here. Okay, so let's try the second graph up here. And I'm going to start with 1, 1. My slope would be 1 over 1, so 1. If I pick a point like negative 2, 1, my slope would be negative 1/2. So if you want, you can take a little bit of time, go ahead and fill out the rest of this. It would be a good time to pause the video. Okay, so I'm going to fill out the rest of our slopes here. And again, as long as the positive ones are going up and the negative ones are going down, that's all they really care about when they look at your slope field. But that's a pretty good slope field drawing. Okay, so let's go to question number 3, which is an example of a multiple choice question. You might see a question like this on the AP exam. 3 says the slope field of a differential equation is shown below. Which of the following equations could be a specific solution to that differential equation? So if you remember what all of these graphs look like, it should be pretty obvious which graph fits this. E to the x is an exponential function. It should look like that. So this curve is kind of going down, right? The slopes are really steep over here and then it flattens out. X squared looks like a parabola. I'm going to skip to D. Sine, remember, is a wave. ln is the graph that goes like that, which matches, right? If I draw in a particular solution, it looks just like the ln of x. Okay, last question, number 4. Let y equals f of x be a particular solution to the differential equation dy dx equals x over y, satisfying 3, 4. So that means we have a point at 3, 4. Write an equation for the line tangent to f of x at x equals 3. We're going to use this line to approximate f of 3.1. So first thing I see is that we need an equation of a tangent line. So to get that, I need a point, which I have, and I need a slope, and I have a formula to help me find slope. So if I want the slope at this point, I'm going to do exactly like we did on the front. I'm going to plug in my point. My slope is x over y, so 3 over 4. And I have my point 3, 4. So now I'm going to write my equation of my tangent line. Y minus y1 equals m, x minus x1. So there's my equation of my tangent line. The second part of this problem asks us to use this line to approximate f of 3.1. So all that means is that I'm going to plug in 3.1 for x and solve for y. So 3.1 minus 3 is 0.1. 0.1 times 0.75 is 0.075, which means if I solve for y, I get 4.075. Okay, so that concludes our lesson. Feel Feel free to go back and rewatch anything that you struggled with or ask me in class if you have any questions.